and a consultant devoted to scientific research, technology development, and technology transfer and teaching. He is a principal investigator of the Computing Lab and professor of computer science at Tecnológico de Monterrey, Mexico. He made his PhD in the University of Oxford. He is associate editor of Quantum Information Processing and a member of the Quantum Economy Network and the World Economic Forum, and distinguished the speaker of the Association for Computing Machinery. His work is aimed at understanding all scientific and society aspects of computation, as well as contributing towards the economic development of modern society based on science and technology. He conducts research on quantum algorithms and quantum cybersecurity. He is co-founder of the field of quantum image processing and the founder of quantum computing in Mexico. So we are delighted to have him here in this event. Welcome.
Thank you very much. Obrigado. Yeah, that's me. Okay, well, I wish I could speak more Portuguese than saying obrigado, hola, but that's my Portuguese so far. I'm truly pleased to be here. Thank you very much all for your time, your attention. Thank you very much to the organizers. Let me start by introducing my data. This is my full name. The title I thought about quite a lot. Was thinking of a more technical, say, title, but since I'm going to talk about a number of topics, some of them quite related to Mexico and the rest of Latin America and Brazil, then I thought it would be appropriate to call it that way. I almost thought about writing quantum random thoughts, but they're not random, so quantum will be fine. Okay, so this is the university I work for, and these are my email addresses. Okay, so that's it. Now let me... I will be best. Yes, thank you very much. Thank you. Okay, let me try this out. Very well, thank you. Okay, so to start with, in case you are interested in downloading both this presentation and several files I'll be talking about over my presentation, then feel free to go to that tiny URL or QR. They'll take you to the same folder in Dropbox. In case you cannot do it now, then the same information will be at the very end of the talk, okay? And I have 1 hour, I understand. Is that right, Renato? So do I have 1 hour? Do I have 1 hour to talk? Okay. For questions. All right, thank you very much. Okay, so now let me start by thanking Renato, Joao, Luis for inviting me, all the staff of this conference, of this marvelous conference. I have to say I'm truly pleased to be, this is my first time in Brazil, and it's also, I found a very welcoming environment. Talking to many of you has been great. So honestly, thank you very much from the bottom of my heart for this opportunity to talk to you and to meet many of you. Thanks to my employer, because, you know, I'm kind of a difficult guy. I'm politically incorrect all the time, so they bear it with me. That's why I like them. Now, I would like to begin just by briefly introducing to you all the university I work for. This is something that I found quite interesting when traveling all over the world, that we actually happen to know very little about each other. So let me introduce 2 slides only about the university I work for. This is the main campus in Monterrey. Monterrey is the one of the capital cities on northern Mexico. The campus I work for is in Mexico City. We have 28 campi all over the Republic, as well as several other in Europe and in South America. As far as I remember, there's one in Argentina, another one in Colombia. About 90,000 students in these 28 campi, a number of undergraduate and graduate programs, particularly focused on engineering, computer science, applied mathematics, data science, and chemistry, as well as biological systems. Okay, well, that's it. I as for the university I work for, hold on. There we go. Okay, so let me start talking about the quantum hardware and software ecosystem, so that we can kind of identify where in the big picture of quantum technologies the work in my research group has been carried out. So as you know, as many of you will possibly know, the quantum technology ecosystem is divided into three pillars: that of quantum computing, quantum communication, and quantum sensing. And my research group, we've been focusing on the development of quantum algorithms. We've also been working a bit on quantum communications and quantum sensors. A few years ago, I was working on the development of quantum radar technology with some colleagues from the research laboratory of the US Navy. But that was just part of our work. We have, over the last 20 years, we have focused on working on quantum algorithms, say from two different perspectives. The first one is that of focusing on fundamental properties of key problems in computer science, like the K-SAT problem or the traveling salesman's problem, meaning NP-complete and NP-hard problems. We want to identify or to determine, to characterize, whatever the verb it is, how to use quantum mechanical properties for solving hard instances of those paradigmatic problems in computer science. And the other branch is looking for applications, as we shall briefly talk about, say, for example, in blockchain and other applied problems. So basically, the idea is to work, the fun part, or I would say the best part in terms of fun, is working on fundamental problems of computer science. But then we need to feed the lion, you see? We need to get money. And to do that, we work on applied stuff. And that's, honestly, this is pretty much the kind of a balance that we have found in my group, given the constraint that we have for having access to money, particularly from the government, to have a balance as for the activities that we would like to perform and that we can perform. Okay, the field of quantum technology and quantum computation in particular, as you know, it's not a purely research area. There's an ecosystem now that includes companies, investors, and as for companies, I'm talking about both global as well as small to medium-sized and large companies, as well as governments. So that basically provides room for many approaches to be followed in quantum technology. Some of us who are interested in that, we can work on fundamental topics. Some other people can actually focus on the engineering side of quantum technology. Some other people who actually know nothing about quantum technology can focus on selling it, okay? On trying to build a market. And these three areas are, as well as many others, are equally important, you see? Working on fundamental research, of course, for every one of us, is key, you know, is part of our lives. But finding the money to carry out these activities, as well as keeping that, you know, in the mind of society, needs us to find ways to apply what we know in points that are relevant to society. Now, this slide, I usually use it to stress a very important property of quantum technology. These guys are the fathers of quantum computation, the first and the second generation of the fathers of this discipline. And all of them are still alive and working, except for Feynman. Now, that's important because there is, and I understand it, there seems to be a huge need to produce applications to require a maturity, a technological maturity on quantum systems for computation, communication, and sensing, which, in my opinion, honestly, we really have to take it easy along those lines. And what do I mean by that? The field is so new that we have many questions for which there are no answers yet, okay? And questions about technological maturity, about the possibility of using, for example, properties like quantum tunneling or quantum entanglement for the development of quantum algorithms are still open questions. They will be open for many years. So we need to realize that the field is young, and that if we expect, say, to have the performance of a quantum computer being equivalent to a supercomputer now in terms of robustness, scalability, and all the other requirements, is honestly, it's kind of expecting too much. Yeah? So that's important in order to evaluate the pertinence and the relevance of the works and the outcomes that we have with our own research, academic research, as well as industrial research. Okay. And these are all companies that you surely heard of. Now, this is the first topic I would like to address. Quantum walks is close to my heart. This is the topic actually I work on during my D field at Oxford. And since then, I've been working on it on a variety of issues. So what I'll do now is as far as I understand, we haven't properly talked about quantum walks in this conference. So with the permission of Professor Portugal, who's next, I'll talk about, who's also an expert, a worldwide expert on quantum walks. I'll talk about the fundamentals of this area, what the meaning of a quantum walk is, what's the goal, and the purpose of using this kind of mathematical structures and physical structures in computation, and then I'll show you some examples of the work we've been doing in my group. Okay, to start with, this is the easiest example of a classical random walk. So walking along a line, and then we have frogging. This is a frog that's going to jump either to the right or to the left, depending on the outcome of a probabilistic system, which in this case is simply tossing a coin. Now, random walks constitute a very important feature in applied and theoretical for computer science, because we can use it we can use this kind of stochastic systems for producing a variety of algorithms. For instance, we can simulate earthquakes by using a particular kind of random walk. That, I'm not that sure how relevant that topic is in Brazil, but in Mexico, it's truly relevant. I mean, Mexico City goes through earthquakes, floods all the time. We actually say half jokingly and half seriously that we're expecting Godzilla and King Kong to have a fight in Mexico City, because this is really apocalyptic. So this topic is truly relevant to all of us back in my country. That's why I mention it. We can also say model attacks in wireless networks. We can use actually random walks to model the behavior of stock prices. This is actually the work or the paper or one of the main papers that gave Fama his Nobel Prize in economics. And we can also use random walks to solve, or say to develop, sophisticated algorithms for solving key problems in computer science. For those of you who are computer scientists, you're actually familiar with this problem, the K-set. For those of you who are not computer scientists, the K-set problem is basically a problem of mathematical logic. And what we do is that we produce an instance, that is to say a proposition, that depends on the combination, on a particular combination of logical variables, yes or no, together with ors and ands. And then the goal of this problem is to determine whether a given instance, whether a particular proposition, those have a solution or not. That is to say, if there is a particular set of values for those variables, for those dichotomic variables, that makes the proposition equal to 1. For instance, this one. This is a very, say, kind of a modest instance. It's got only 6 binary variables. It's composed of 27 clauses. A clause is defined by having logical variables glued with ors. So you see, the goal is to have each one of these clauses, what we have in parentheses, in between parentheses, equal to 1, so that the result of having a 1 plus 1, 1, and 1 and 1, meaning this ends, makes P equal to 1. So all we have to do is to find a particular value for the logical variables that we have on each clause. At least one of them has to be equal to 1, so that the AND of all of them produces a 1, okay? So what would you say? Is there a solution to this? Is there a particular set of values for this proposition that satisfies the requirement? Yes or no? That's the question that we have to pose. Well, this proposition I designed it by hand in order to make sure that it had only one solution, which is the one that we have there. But you see, even in a modest instance that has only 6 binary variables and a modest number of clauses, it's hard to tell whether the instance has a solution or many solutions or just one, you see? So the K-set problem, in addition to being a fundamental problem in theoretical computer science, can also be used to model many things in industry, finance, and the like. So that's why it's important to study. One of the best algorithms developed so far for solving the K-set problem, of course you can quickly realize that a brute force solution to the K-set problem has an exponential computational complexity to the end, where n is the number of binary variables. But we can use stochastic systems, and in particular, we can use random walks to produce, say, a less inefficient algorithm. An example of that is Schunin's algorithm by Uwe Schunin, its creator. that basically requires a bit less than 2 to the n power to produce a result with a certain probability. So the point I want to make, and aside, the technicalities of this algorithm, is that we can use random walks to produce less inefficient or more efficient, whatever you want to say, algorithms for solving this kind of problems. Okay, so and that was actually the inspiration that computer scientists had for thinking of a quantum version of random walks. Quantum walks was born as a result of the work of some physicists, actually here in Brazil. And then when computer scientists realized that there was a quantum version of a classical random walk, then we thought, well, why not producing some algorithms? Right, now the fundamentals of quantum walks, surely remember that in stochastic systems, we have two kinds of random walks, discrete and continuous, depending on the way that we basically use time or use the variable that define the evolution of those systems, okay? In quantum walks, we have exactly the same. We have a discrete version and we have a continuous version. And the most simple version of a quantum walk is that of tossing a coin, but this coin is gonna be a quantum coin, and there will be a walker, which will be the a quantum walker, which will be the quantum version of the frog that I just showed you. And the main difference between a classical random walk and a quantum walk will be that as we shall see in an example, that in a classical random walk, the walker jumps from one side to another, depending on the outcome of the probability system that we're using for the evolution of the system, meaning for the dynamics of the system. While in the case of a quantum walk, we're going to have a superposition of both the walker and the coin. The coin is not an essential element. We can actually define the notion of quantum walk without coins, but the coins actually help to make a parallel with the behavior of a classical random walk. So that's what we have in the next slides. Before getting into the example that I'm sure you're going to like, let me say that quantum walks, in addition and in contrast to the behavior of classical random walks, actually constitute a universal model of quantum computation. That's a very important property of quantum walks that has no parallel in the classical world. In the classical world, we use random walks to produce sophisticated algorithms, indeed, but the mathematical tool itself does not constitute a universal model of computation. And what that means is that we cannot build any algorithm that we may possibly think of by using a classical random walk. While in the case of a quantum walk, any quantum algorithm you may think of in the circuit model, in the quantum adiabatic model, whatever you can think of in terms of quantum, can also be written as a quantum walk-based algorithm. Now, that's terribly hard, as we shall see shortly in the when we address that topic and we talk about the research that we've been doing in my group along those lines. But in principle, it's possible. So that's a property that has no parallel in the classical world. So let me show you the example that I have. All this topic was just said about the discrete nature. Oops, sorry. Hold on. About the discrete nature of quantum walks and also about the continuous nature of quantum walks. Depending on the way we measure time, we shall decide how we call them, discrete or continuous. Now, the example that I have is right here. Suppose that I have a system that has a definite initial condition for both the walker and the coin. So the classical equivalent, for instance, would be to have a frog sitting, say, on the side number 0, and then having a coin that, depending on the outcome of the coin, I shall move either to the left or to the right, okay? So that's what this means in terms of a quantum mechanical system. And then the operator that we have here, the Hadamard operator, is the coin operator. It's basically the operator that will put the coin in superposition, so that depending on the actual structure of that superposition, we shall scatter the walker along the line or along the topology, along the graph that we choose, okay? Now, these are the first 3 steps of a discrete quantum walk. In case you actually want to reproduce, the calculations back home, then you got an example of how it works. And now, let me show you. You know these guys, don't you? I spent a lot of time working on it, so hopefully you like it. So we have Chavez and Don Ramon first on a classical random walk. So Chavez tosses a coin, And then depending on the outcome, Don Ramon will move either to the left or to the right. Maybe you cannot read it, but here I have on the upper left corner of the slide, I have heads and tails depending on what we get. So heads moves to the right, tails moves to the left, heads right, tails, 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 and there we stop, okay? So that's the behavior of a classical random walk. Now the behavior of a quantum walk will be, we have an initial condition, as it is indeed the case with the classical system, but now Don Ramon will actually split, will scatter over the line, depending on the actual superposition produced by the coin that Chavez is not really tossing, he's kind of putting into superposition by means of a quantum operator. So if we wanted to find out after a certain number of steps where Don Ramon is, what we would have to do would be to measure the system. And then the measurement of the walker along a quantum walk, either on a line or a circle or any graph we may think of, will produce, and this is a very important property, will produce different probability distributions depending on the initial condition, which is why we cannot say that the quantum walk is a Markovian system, and also depending on the actual parameters that we have on both the coin and the shift operator. Examples of that kind of probability distributions are what we have here. So you see the only difference between, as for the mathematical structure of the quantum walk that produces this probability distribution and the one on the right is the initial condition of the system, okay? So that's, that in my opinion, provides a quantum programmer, people working on the development of quantum algorithms, an additional set of richness, so to speak, you see, of different parameters, of different probability distributions that we could use for designing new algorithms for either theoretical computer science problems or applied computer science. Okay, so that's this is my introduction to quantum walks. Now let me talk about my research, the research in my group. So this is the first topic, and this is a topic we've been working on over the last 3 years, which is running quantum walks on genotype networks. Now let me introduce some information about this stuff. First of all, the goal of this research is to explore genotype networks using quantum walks, possibly finding potential advantages with respect to exploration using classical random walks. So we shall define what a genotype network is in a sec, okay? But the goal is, or say abstractly speaking, what we have is a graph composed of thousands of nodes and edges. And what we want to do is to run on those graphs both classical and quantum walks in order to identify some properties that happen to be biological properties that are translated into mathematics, and that's why we can actually detect them using quantum walks. The long-term goal of this research is to assess new ideas from the field of biology and to produce new computational tools to study biological data and processes. This is quite an important matter because you see, in order to run this kind of research, in my opinion, it's highly convenient not only to work within the realm of computer scientists, physicists, and mathematicians. We also need to have, and it's very relevant to have biologists on board so that they can actually identify what matters, what not, okay, and provide their insight. So actually, this research began that way. By having a chat with a friend of mine who's a biologist, he said to me, there are open questions as for the nature and the mathematical modeling of mutations. So the mutation is a concept defined, from the theory of evolution by Darwin, but the experimental data that biologists have and have had for several years now, it's not that it contradicts the theory of evolution, it doesn't, but it does give room to having a more, say, an expanded definition of what a mutation and what are the fundamental properties of a mutation. For instance, it's kind of a common wisdom among the biologists who follow the Darwinian evolution understanding that mutation is a process that happens randomly. And by randomly, what that word means precisely in biology is by uniformly random variables. Okay? However, there's evidence of several living organisms that can actually adapt themselves very quickly to their environment, for example, bacteria. Yeah? And they actually have mechanisms to kind of, I wouldn't say deliberate, but pretty much, almost, to make changes very rapidly on the structure so that they can survive. Something that we humans cannot do, but very small organisms, they can do that. And the question is why, on the one hand, meaning what's the biological and the chemical mechanisms that allow them to do so, and also how that new information fits within the great picture of evolution theory. So by doing this work, we're trying to provide answers. For example, one of the things that we're focusing on, in addition to this research, is to produce a quantum mechanical / computational model, algorithmic model of a mutation. We want to understand biology from a computational point of view. Because it's usually the case that biologists think of mutations as a kind of a black box. So you got some inputs, you got some outputs that could be described either in a deterministic fashion or by means of a stochastic system. But what's inside the box is an open question. Okay, so we would like to provide some answers to that. Very well. So that's what we do. Some definitions of this research. A genotype is basically the genetic constitution of an individual organism, and then a genotype network contains all the. Think of the following. This is the best way to describe this is as follows. Think of a graph where each node is an individual, okay, and going from one node to another is equivalent to having one mutation, one punctual mutation. That is to say, a change in the DNA of the individual from one point to another. So having one change in the DNA is equivalent to going through an edge from one node to another. Okay, a genotype network contains all the genotypes that have the same phenotype. What that means is that a genotype network contains all the mutations that happen not to produce any physical change on the organism. For example, we all go through a number of mutations due to solar radiation, a number of things that we go through in our lives. But in most cases, we don't notice that we went through a mutation because there's no physical change on our bodies, okay? So all those mutations that have no effect, no physical observable effect on the body or the physical structure of a living being, they go inside a genotype network. And then the genotype space is a set of networks, okay, that contains all the individuals that may or may not have changes on their physical structure based on a mutation, okay? So what we want to find, for example, one of the questions that we have is, what are the biological expressed in mathematics for computational properties? What are the conditions that are to be fulfilled so that the organisms of a species can have changes in their DNA without actually having changes in their bodies? So that, for example, could actually lead to hints about changes in DNA that do not cause cancer, okay? And by the same token, we could actually ask the question of what's the characterization of those mutations that would make us jump from one genotype network to another. That is to say, to have a mutation that actually provokes a change in the physical structure of the living being. Okay, so that's what we do, and we chose quantum walks for two reasons, meaning as the vehicle, for analyzing these graphs. The first one is that some previous work by several research groups, mostly based in Germany, they've been running classical random walks over these graphs, okay, over graphs of several species like mice, fungus, and others. So we wanted to compare the performance and the precision of those random walk-based experiments with quantum walks. And there's another reason for that, which is that a mutation, in principle, has to be at least partly a quantum mechanical process. You see, the size of the elements that constitute the basic components and mechanisms of a mutation are so small that, for example, there are some free protons that we have in DNAs that actually may provoke a mutation. And there's a very famous paper in the field which is entitled proton tunneling. And it sounds weird because we may think of electron tunneling, but it's not. It's a proton. It's a proton of a hydrogen atom that actually basically goes wild and goes through a tunneling process. So the point I want to make is that we thought of quantum walks because we thought that it would be the appropriate vehicle to reflect or to kind of exhibit some parts of the nature of mutations themselves. So these were the two, say, arguments or motivations that we had for running quantum walks. The result, well, this is the mathematical definition of a continuous quantum walk, in particular applied to this problem. And there are a number of papers that we have produced along these lines. This first paper that we published at the Royal Society Interface is the very first paper that we published on this. It's kind of a toy model in the sense of the number of on the size of the graphs that we used. They were kind of modest because we were using modest computational systems. And what we found as a result in this of this research was that the graphs that we used, or the genotype spaces that we had, were so small that actually there was no evidence of a computational speed up provided by quantum walks, but we certainly produced a model that was precise enough to reproduce the experimental data that of those species. So we were on the right road because we managed to produce a quantum mechanical model that reproduced precisely, faithfully, the results, the experimental data that we had about these species. And then, now let me say something about this. The development of quantum walk-based algorithms has an additional problem to developing an algorithm based on the quantum circuit, which is the fact that there is no quantum computer available nowadays that actually runs natively a quantum walk. All the quantum computers that are available now run quantum circuits, okay? If we think of D-Wave technology, they got a restricted set of algorithms known as quantum annealing algorithms, but no quantum computer is available now. I mean, it hasn't been produced, so they can run natively quantum walks. So we can either translate quantum walks into quantum circuits, which is an open problem how to do it efficiently, or we could simulate quantum walks on high-performance computer platforms. We chose to do the second, to follow the second rationale, which was to simulate running quantum walks over a large genotype space for 3 species. And as a result, and then to do that, we received a grant from IBM. So thank you very much, IBM. We had access to their HPC platform for 2 years, and we produced very interesting results thanks to that grant. Okay, now, hold on, let me go back. Okay, there we are. So we run these simulations. We produced this paper, which is a new definition of the notion of heating time for continuous quantum walks, based on the notion of a Poisson process that works very well for the problem at hand. We published this paper last year, and then we ran computer simulations of both continuous time walks, and random walks over the same genotype spaces, but the large ones, meaning running both on the HPC system of IBM. And what we found was that the quantum heating time, meaning the quantum heating time having as definition of quantum heating time that we published a year before, was faster than the corresponding classical heating time. And it's faster in terms of this ratio, okay? So we're doing well. I mean, in both cases, as for the first paper and these other 2 papers, we were working under the assumption of closed quantum systems, okay? But mutations happening simply because of, let me put it this way, of errors in the information processing systems that the human biology or other organisms have. Now, many mutations happen because of the externalities, because of the exchange of information or the effects that the environment has on the DNA of a species. That's why our current research is basically, well, we spent quite a lot of time on this Hamiltonian. It's a Hamiltonian that comprises many of the effects that one would expect to have on DNA due to radiation, temperature, salinity, and the like. And the results are now under peer review. We got it, for those of you who are interested in this field, they are available, the preprint is available at the bioRxiv. And basically the contribution of that paper is, on the one hand, a full description of a Hamiltonian that includes a Hamiltonian that describes the physical effects that may provoke, that may have as a consequence a mutation on the DNA of any given species. We have parameterized that influence that the environment may have on the DNA, so that we don't have to know all the details of the interaction of the environment with the DNA, but only the relevant features, the relevant parameters that would allow us to understand what's going on and how the mutation is going to happen. So that's the paper, and that's it for this topic. Okay, I still have how many minutes? Okay, about half an hour, right? Or 20 minutes, a little less. Okay, very well. Fine. Now, next step is, it's a number of slides that I have here, but the topic I already talked about, which is the universality of quantum computation. See, universality is a fundamental property of computer science, which basically consists on the capacity of a mathematical model of a computer to simulate the behavior of another computer. For example, think of the following. The fact that we all can write a computer program, say in Python, no matter the particular hardware that we use, no matter if we're using a Mac computer, Lenovo, or whatever it is actually a consequence of the notion of universality applied on both hardware and software. It doesn't matter whether your Python interpreter is running on a Mac or an IBM or whatever it is, any hardware that you may have, okay, it's going to run pretty much the same. Not exactly the same, but that not the same is not due to fundamental differences of the behavior of an interpreter, but to difference in the implementation of those interpreters, okay? So that notion of universality, being able to simulate the behavior of one machine using another machine, also goes into the quantum realm. And as a result, we know that the quantum circuit model, the quantum adiabatic computational model, and the quantum walks, they three constitute universal models of quantum computation. So what that means in practice is that if I write a quantum walk-based algorithm, in principle, I must be able to translate, to transform, to produce a new algorithm based say, on the quantum circuit model that does exactly the same as my quantum walk-based model. Now, algorithm, sorry. Now, doing that, I said in principle because it can be terribly difficult to do so. As a matter of fact, it's an open problem in quantum computational science to know how to transform an arbitrary quantum walk-based algorithm into the quantum circuit model. We don't know how to do it efficiently for an arbitrary algorithm. So that's a topic we've been working on in my group. We have produced a number of papers. I'm just going to mention one of them, which is this one, circuit implementation of discrete time quantum walks via the shunt decomposition method. We also produced another paper that was published also at the Quantum Information Processing Journal using Krauss operators. So the goal of this research is to build mathematical methods that would allow us to transform a quantum walk-based algorithm into the quantum circuit model. And there we go. It's still an open question, but this is our contribution to the field. Okay, so research horizons in quantum walks, and with this I'll finish this part of my talk. We need to do a number of things to keep the, I would say that the field is in very good health, but in order to keep it in good health, there's a number of topics that we need to address. In particular, we need to find killer apps, that is to say, killer applications of quantum walks. Now, numbers to be remembered in this field, of course, Professor Portugal is the one and the first, and several other people like Professor Petruccione and several other colleagues that are mentioned right here. Okay? References in this field, Professor Portugal's book on quantum walk research algorithms. This book is actually, it's got a chapter by Professor Nori Kono from Japan on the definition and some properties of quantum walks. It's a highly mathematical chapter, so it's a pleasure to read it. This is a review I wrote a number of years ago. A book that I also wrote on quantum walks many years ago, too many, I would say. And that's it for quantum walks, okay? Now for quantum cybersecurity, and I'll finish, this is gonna be short. This is a topic we've also been addressing in my group. And see, there are many links between quantum computation and quantum information science in general and cybersecurity. Maybe the most important one is a threat, which is the fact that, as you surely know, in principle, we could use a quantum computer running Shor's algorithm, basically to break RSA. And RSA is a public key cryptographic method that we use all the time because it's very popular. Whenever we buy something online, we're most likely using a variant of RSA. So RSA is used all over the world. It's a very strong and popular cryptographic method. And in principle, it could be on the vulnerability scenario in between 10 and 15 years time. Okay? So basically the problem is that for someone having access to a large enough and to robust enough quantum computer, they could break RSA. Now, if people wanted to break RSA, for stealing my credit card number, I don't think so. I mean, they're not going to get that much money, okay? But the thing is that they could have actually massive attacks that would threaten, the actual infrastructure, both physical and virtual infrastructure of a country, for instance. So there's a serious worry in the corporate world and in the government world for understanding the actual consequences of Shor's algorithm and for finding methods to minimize the negative impact of that technology in the cybersecurity systems. Along those lines, I co-wrote a paper. Well, there are two things I would like to say. Along those lines, there's a very important and serious effort by NIST, the National Institute of Standards and Technology of the United States. They just published about 1 week ago, something like that, a set of standardized and certified post-quantum protocols. Okay, what that means is that this set of protocols that we would actually find if you click on this link will be a set of protocols that, as far as we know, are immune to the attack of quantum computers using Shor's algorithm. Might be the case that tomorrow someone else comes, a bright guy comes with the idea of how to use a quantum computer for attacking these new protocols, but so far they are immune. And as you surely know, cybersecurity is kind of it's a give and take area in which people have advances, and then suddenly someone bright comes and shows that advance was not that significant. It's just a matter of time to break that protocol, and there it goes. It's kind of a spiral. So that's why it's quite important to learn about the updates in this field. Okay, guys. Now our work is contained in this paper that I co-wrote with Quantinum, this famous quantum computer company, and the Inter-American Development Bank. What we did was to show that we could use quantum technology to protect several components of blockchain, because a blockchain is basically a bundle of cryptographic protocols, and several of them actually are based on the conjectures of the mathematical difficulty of breaking RSA. But a quantum computer would actually make those conjectures invalid. Okay, so we show that by using quantum technology, we can actually protect blockchain from the attack of quantum technology. So this is what this paper is about. Okay, guys. Some reflections on the development of quantum markets and quantum workforce. I think, as I said in the beginning of this talk, that there is room for many, many different opinions and works in this field. Of course, scientific and basic research is fundamental for the advancement of our discipline. But that, together with the creation or the development of a workforce and a quantum market and a quantum ecosystem, is fundamental to keep the field alive. Okay? Now, these are some reflections that I actually talked about back in December in a meeting that we had at the Vatican, a meeting organized by the Pontifical Academy of Sciences. And well, I think I didn't say this to you, but in addition to being a professor and a consultant, I'm a businessman. I own 2 companies, and I work as a consultant for several organizations in Mexico, in Europe, and the United States. And then, due to that, I have a kind of a good idea of the steps that we could actually potentially follow, at least, in order to further develop the field, and also to have a workforce capable, of tackling the problems that we shall be facing over the next years. And in addition to that, the tools that we need for advancing the field. For example, in my opinion, the quantum circuit model, or the quantum walk model, or the quantum adiabatic model is fine for producing, say, quantum algorithms so far, but it's unfeasible. I mean, the mathematical tools that we have in those platforms or in those models of computation are too primitive, for the development of quantum technology as a field of industry and as a workforce. Let me show you why I say this. You might not be able to see, the in full detail, in full detail this graph, but here I have, on the left-hand side, I have the code that we need in assembly language for the 80x86 microprocessor family for writing hello world. So a number of lines, okay? On the upper side or right-hand side of this graph, I have the code that we need in Python to write hello world, just one line, okay? And here I have, as an example, the Minecraft, the kind of environments that my students use to write programs. So what we call serious gamification. So the tool is fundamental for the advancement of a discipline. Think of, the typical example, think of multiplying a 6-digit number in Roman numerals, okay? That's gonna get hard. We will eventually do it, yes, we will, okay? But the digital, the Arabic system is much better for doing exactly the same job. So the same applies here. Okay? Very well, I think I should stop shortly. Yes, I should, huh? Okay, fine, thank you very much. Okay, let me finish by addressing two topics very quickly. The first one is the work that we've been doing at the World Economic Forum along the lines of, along several lines. Let me start with this. The World Economic Forum is an organization that is really focused, of course, as its name implies, on the use of technologies and new ideas for the development of markets, okay? And the development of companies that could be at a global scale or at a local scale. I've been privileged enough to work, to be a member of two think tanks of the World Economic Forum for the last 2 or 3 years, okay? And we've been focusing on the topics of cybersecurity and quantum technology. And what you will find here is a set of different white papers that have been published since 2021 or 2022 on different aspects of quantum technology. For example, there's a series actually of papers that we have written, and I've been privileged enough to be a co-author of, on the topic of quantum security, which is to say the impact and the ways to, the impact, the negative and the positive impact that quantum technology may have in cybersecurity and computer security in general. There's another topic which is quite important, particular to our societies, which is this paper, the Quantum Economy Blueprint. This paper contains, say, the major guidelines for a country or for a region to develop national strategies for the development of particular aspects or particular subfields of quantum science and quantum technology. I mean, in other words, to make those countries capable of developing their own capacities in quantum technology and therefore being part of the great business area which is to come along these lines. In Latin America, for instance, the only country that actually has a national initiative is Brazil. Mexico doesn't have one yet, okay? Even though we have the critical mass in terms of scientists, the companies, and all we need, all the ingredients are there, but we haven't produced it yet. So one of the questions that this document tries to answer is, why is it that there are some countries that even though they have all they need for building a national strategy on quantum technology, they haven't yet? Yeah? So if you're interested in that part of quantum studies, so to speak, you can download all these papers, and actually you will find them on the folder that I talk about at the beginning of this talk. Okay, so that's the first thing I want to say. There's a Mexican quantum ecosystem that if you're interested in learning what we're doing in terms of big projects, national projects or region-based projects, there's a paper that you can download right here. It's in Spanish, so you can read it. Reading it is easier than listening. Okay, this is some slides about my lab. I've already talked about, so I won't spend much time about this. Just that we founded, some things I would like to underline about my group is that we founded the field of quantum computation in Mexico 20 years ago. We specialize, as I said, on the development of quantum algorithms for both fundamental aspects of theoretical computer science and applied aspects like the blockchain thing I talk about. We have extensive experience on technology transfer and knowledge transfer to the industry, both in the United States and Mexico. And these are some publications that we have. If you're on Facebook and you want to talk about quantum technology, feel free to join the Quantum Information Science and Technology wall in Latin America. So you can identify the lemur. It's the easiest way to find what the wall of this organization. This is a course that I recorded in 2017 on the fundamentals of quantum computation in Spanish. I did it because at that time, well, actually, this is indeed the case nowadays. Most of the information, most of the books, papers, and blah, blah, and educational material produced to learn quantum computation and quantum technology in general is written in English, which is fine. It's the lingua franca of science and technology. But we also need to have some production in our own languages, in Spanish, in Portuguese, so that the students that we have who are not, say, competent enough in English, that doesn't become a barrier for learning the fundamentals of this discipline. That's why I recorded this course. This is the website of my group. If you have papers, incoming papers, then please send them to Quantum Information Processing. I'm an associate editor of the journal, and Professor Portugal was a guest editor of a special edition that we had on Latin America, on quantum information in Latin America. So it's a good journal, so send it there. The World Quantum Day, and that's it. I want to finish by some conclusions that will take about 20 minutes time. Take 1 minute. There are many conclusions that we may have, but the first one is this. This is the first computer for which I wrote a program when I was a child, 9 years old. And this is the QPU of the D-Wave machine that was available at NASA when we had access. My group was the only group in Latin America that had access to that machine from 2014 to 2018. So this happened in a bit less than 30 years' time. That's very much what's likely to happen to young people, okay? Maybe twice or thrice in their lives. So as an educator, because at the beginning and at the end, I'm a professor, I'm really worried about and really busy about thinking what we have to do in order to keep learning about these topics relevant to our young people. But that's one conclusion. And the other one is that we can, and in particular in Latin America, technology can be a vehicle for the development of a society in which we all fit. In Mexico, I'm not sure about what the current scenario is in Brazil, but in Mexico, we have a very serious problem with organized crime. Okay? And organized crime, the energy source of the organized crime is young people. So we need to find a way to make our young to turn their heads, to look at the school as a viable option to grow and to have a decent life, as opposed to what happens now to many people, to many young people in Mexico who think of organized crime as being the only way out of poverty. Right? So science is not only for the development of our own intellect, or let me say it because it also happens for the enactment of our own egos, but it also and mostly helps to develop a healthy society. So that's what it is. Thank you very much for your time and for your attention. These are the links that I promised would be at the very end of the talk. And any question that you may have, please feel free to say it. Thank you.
So, and time for question now. Any question?
Hello, Salvador. Thank you for your very nice talk. And you do a lot of things. So congratulations. Okay. About D-Wave quantum computers, you mentioned that, if I understood correctly, you mentioned that it's a kind of rudimentary technology. Why? And do you know some example in which quantum annealers can be useful, or in particular example nowadays in which it's possible to succeed?
That's a very good question. Thank you very much for it. I mean, I'm going to be very open about it. I think that quantum annealers are a fantastic tool, a fantastic theoretical tool for for attacking, of course, optimization problems. But the technology that we have nowadays makes me doubtful about its viability. On the one hand, the technology that we have now solves only one problem, and then we have to translate any instance of an optimization problem into an instance of that problem that the machine can solve, which is in itself an NP-complete problem. So we do it by heuristics. But then the question here is, what's in principle the advantage of using such a machine if the very translation of the problem I'm interested in solving requires solving an NP-complete problem or using heuristics, which is what I would do anyway with a classical computer. So that's one thing. And then I haven't used quantum annealers for a number of years now, but the experience that I had when we had access to this computer was that it was truly faulty. There was a huge need for example, for being resistant to small changes in temperature in order to produce fruitful results. So it might be the case that already gone through that maturing process. I don't know, because I've been told explicitly that the organization that produces these computers is not interested in Latin America. So we don't have access to that. When we had access to these machines from 2014 to 2018, it was due to the really, really generous effort by NASA and Google that basically gave for free 20% of the time the machine was installed at the Ames Research Center. But then the federal administration in the United States changed, and with that change came the very end of this of this access. Okay, so since then, so that's it. That's what it is. We haven't had access to these to the new versions of those machines for the reason I just explained. So I don't know whether we've already gone through that maturity process. But the fundamental problem that I see is that it's not clear to me what exactly is the advantage in principle apart from being lucky enough to solving a problem using heuristics, which is basically what we do with classical computers. Thank you for the question.
There is a question from the internet from Professor Rubens Ramos. What is the future of quantum image processing? Do you see any real application of quantum image processing in not so long future?
Thank you very much for that question. Quantum image processing is a field that I co-founded when I was reading for my DPhil. And yes, indeed, I mean, that question I have actually posed to myself over the last few years. And we have actually written 2 papers on that. I suppose that he's seeing me through that camera, okay? Yeah, we've written 2 papers about, along those lines. The last one is actually available right now for free. There's a free access, temporary free access, at the website of the ACN Transactions on Quantum Computation, and the title is 20 Years of Image Processing, or Quantum Image Processing, Reflections over the first 20 years. Now, to answer the question is that I think that the future of quantum image processing is, or at least the future that I can see, is in 2, say, fields. Oh, thank you. The first one is that of integrating quantum image processing algorithms in firmware, in devices like cameras, like photographic or video cameras. The very process actually of collecting the data that we need for producing a digital image is a quantum mechanical process. So the collection of photons and the way that the information is collected and then processed is a quantum mechanical process. So if we have quantum image processing algorithms installed in the equivalent of classical firmware, but for quantum data, then that would be, I think, quite a fruitful area, for example, for medical research, or other fields that I cannot remember now, but medical research is one of them. So that's one thing. And the other area in which I think that quantum image processing could be fruitful would be to be used as a complementary set of algorithms for already existing digital algorithms in a hybrid environment. That's what I think. I don't understand that there are, how to put it? I mean, there's a lot of information about quantum image processing methods for storing data, for retrieving data, and there are some fundamental problems that we still have to solve if we think of quantum image processing as being kind of a, I wouldn't like to say replacement, but kind of being a field that can actually reproduce the effects, the processes, and the maturity that digital image processing has nowadays. But I don't think that this is the right way to go. In my opinion, the integration of quantum image processing algorithms into hardware, as I just described, in cameras for both photograph and video, as well as having complementary environments or complementary scenarios for both digital and quantum algorithms working in the same hybrid environment would be the right way to go for the field to become more fruitful than it is now. Thank you for the question.
There is a follow-up question by Rubens. Do you intend to make a quantum walk on DNA chain in order to find a specific sequence of nitrogen bases, ATGC?
Good question. Not now, but in the near future, yeah, we're thinking of doing this kind of experiments. And not now, because now we're focused on working on genotype networks and this model of mutation that I just described, but most likely, say, in 2-3 years' time. Or if I get money, for having one more PhD student, then might be faster.
Okay. So thanks a lot for your talk. Thank you very much.
Thank you very much.
Bem, boa tarde, pessoal, novamente. Vamos dar sequência aí ao VSIC. Para mim é uma honra poder estar apresentando aqui essa última plenária, né, do VSIC, do Renato Portugal. Bem, o Renato dispensa comentários, né, com relação à pesquisa, às publicações, etc. Então, vou tentar falar o mais breve possível, né, e tentar falar de um lado do Renato dessa questão de ter esse poder, por exemplo, de aglutinar, né, as pessoas em torno, e não só da física, mas como da matemática, das engenharias, e dizer que é uma honra poder ter o Renato como uma pessoa parceira em vários sentidos, né, colaborador, pesquisador, organizador de eventos, etc. Né? Renato, pesquisador de CNPq, Renato, sócio da SBM, da SBMAC, da SBC, publicador de mais de 120 artigos, trabalhos, foi organizador do terceiro VSIC, né, em 2010, no LNCC, enfim, né? E obrigado aí, Renato, por acreditar no VSIC e por acreditar nas pessoas, né? No sentido de colaboração, de ter essa parceria, agora com as empresas. Então, você... Eu não sei se eu posso falar isso aqui, mas é porque está filmando, né? Enfim, obrigado, Renato, por tudo aí. E só aproveitando, né, rapidinho, falar do sucesso do VSIC, né, que vocês sabem, nós já temos 2 candidatos fortes, né, Renato, pela primeira vez em sequência para ter a realização do VSIC. 2025, professor Eduardo Duzione, na Federal de Santa Catarina, então já vai anotando aí na agenda. em 2026 o João Marcelo lá em Salvador. Então, já aproveitando a propaganda aí da fama do Renato e que é um entusiasta desse evento. Boa palestra.
Obrigado pelas palavras. Eu vou falar sobre algoritmos quânticos, vou fazer uma revisão. Vou falar dos algoritmos. Sorry. I'm going to speak about the basic quantum algorithm, and then element distinctness, HHL, and then variational quantum algorithm, and then quantum walk-based search algorithm. So a large part of my presentation is a review. So what are the basic quantum algorithms? We can tell that are the algorithms that were developed in the 90s. Dotiosa, Bernstein-Vazirani, Simons, Shor. Shor made two algorithms for factoring and discrete log. Phase estimation algorithm and Grover's algorithm. So I made an advertisement here of my booklet, about 120 pages, describing all those basic quantum algorithms in a pedagogical way. So let me start about the basic quantum algorithms. So I'm going to start by defining query oracles. We need to query oracles and use them as black boxes. What is the definition of an oracle? So oracle is a function, is a collection of binary functions that takes an n-bit input to and produce an m-bit output. The function has some hidden property and that we aim to discover by querying the oracle as a black box. So we don't look at the details of the oracle. We can only query it. So m is the number of qubits of the first register and m the second register. So the size of the second register in most of them is 1, except for Simon and Shor. And what are the oracles of those problems? So Dotiosa, you have an oracle that is either balanced or constant. You have this promise. Balanced is when the number of ones and zeros coincides at the image. The oracle for Bernstein-Vazirani is a linear function, like this here. The oracle is a linear binary function, a generic one. So the quantum computer can implement linear functional or non-linear function. There is no problem of implementing non-linear function, and this discussion appeared in the Newton's talk, so there is no problem. Linear comes from linear algebra, not from linear functions. So Simon problem, the oracle is this one. F of x is equal to f of y if and only if x or y is either 0 or s. So s is the hidden property. We have to find out what is s. The oracle for sure is a periodic function, and we want to discover what is the period. Grover, the oracle is a function so that f of x is equal to 1 if and only if x is equal to x0. Let me change the battery here. Can you change the... So the structure of all those basic quantum algorithms is the same. Is showed here in this circuit at the bottom. So you have two registers. and then you apply Hadamard for the first register, and then you apply the oracle that goes to in both registers, and then you have some quantum post-processing. Okay. And so the first register of those algorithms is almost all of them is n, except short that's 2n. While the second register, the size is 1 qubit, except Simon and Shor that have n qubits. What is the quantum post-processing? For Deutsch user, Bernstein-Weiser and Simon, the post-processing is Hadamard tensor n. For Shor factoring is the inverse of the Fourier transform applied on the first register. And the quantum post-processing for the Grover is 2 cat d, Brad d minus I, where d is the uniform superposition. So you can see that we can put all those algorithms in one format. This K here means how many times you have to repeat these dashed boxes. In most of them, you do it only one time, while in Grover algorithm, you repeat square root of 2 to the power n. And here is the recipe of implementing a function, the oracle. And here you can choose any binary function or a collection of binary function that can be linear or nonlinear. So moving ahead. So which one has entanglement? So it depends, usually depends on f. Dot user. Depends on f. If f is constant, there is no entanglement at all. If f is balanced, it depends on f. Can be entangled or not. During the algorithm, you can have entanglement or not. Bernstein-Weiser, it depends. No, never. It never has entanglement. Bernstein-Weiser has 0 entanglement during the whole algorithm. And the goal is to find S. That's the hidden property. Simon algorithms. It depends on the Hamming weight of S. If the Hamming weight of S is 1, there is no entanglement at all in Simon's algorithm. If it's larger than 1, you have entanglement. And then the entanglement keep increasing, the amount of entanglement, until you get maximal entanglement when the Hamming weight of S is equal to n. Sure. The function is periodic, and yes, there is entanglement. Grover, yes, there is entanglement. And now the computational complexity of those algorithms. Dot user, the quantum version is O of 1. And here we count the computational complexity as how many times we use the oracle. Is O of 1. There is no gain in comparing two classical algorithms. If you allow a randomized classical algorithm. The first quantum algorithm that has gain was Bernstein-Weiser. The quantum case is O of 1, the classical case O of n. So there is a linear gain. It's not an exponential gain, it's a linear gain. But it's impressive that it is a linear gain and there is no entanglement at all. So entanglement is not necessary. It's not absolutely necessary for gain of complexity. The first exponential gain came from Simon's algorithm. The quantum case is O of n squared. So recall that n is the number of qubits of the first register. So it's the size of the input. And the best classical randomized algorithm is O of square root of 2 to power n. So this is an exponential gain. Here n squared appear because you run the quantum part once, you get a result. That's not enough to find S. So you have to rerun n2 squared times, and then you find S. On the quantum cases n2 to log n, but this n2 depends on which way you are implementing the modular exponentiation. You can improve using Karatsuba method, and then you can improve this power 2 here. The best classical is sub-exponential, is exponential of square root of n. So square root of n is called sub-exponential, while this one here is called exponential. Because here you have 2 to power n over 2, while here we have 2 to power square root of n. But it is still not polynomial, and not super polynomial. It's worse than super polynomial. That's the best known classical algorithm. No one knows if you can improve that. Grover algorithm is exponential, is square root of 2 to power n, while the best classical algorithm is 2 to power n. The Kitaev's phase estimation algorithm is a little bit different, and the goal is that given unitary U and one of its eigenvector, try to find the phase of its eigenvalue. So written in this form, the phase is between 0 and 1. So we want to find the phase with n binary digits, so the size of the first register must have n qubits. And when you make the measurement here at the end, you find those n binary digits of the phase. So the algorithm works as those controlled powers of U. So the U that you are using here, you put here, and there are n of those controlled operations. So the number of controlled operation here is small, is n, but the complexity of the algorithm depends on how you implement U. If U is efficient, the whole algorithm is going to be efficient. So, and this part here can be thought as the oracle. This is the description of this algorithm using as input an eigenvector, but you always use this algorithm putting as input some well-known vector here, like the uniform superposition. Grover's algorithm has some follow-ups that is a good idea to show. So Grover's problem is you have this Boolean function that has this promise, and then we want to find x0 by querying f. And Grover has this very nice description using reflections about hyperplane. So when you apply the oracle, you start from the uniform superposition D here, and there is a reflection about the hyperplane orthogonal to the marked element. When you apply the Grover operator, you have a reflection about D, and then the vector go up, and then it approaches x0. So in Grover, you start on a non-entangled state, and the entanglement increases, and then you want it to decrease in order to find x0. The follow-ups of Grover's algorithm are the generalization of Grover's algorithm done by BBHT, Bennett, Brassard, Hoyer, and Tepp. The quantum amplification, the quantum amplitude amplification by the same authors. The quantum counting, that means you have a database with a lot of marked elements, and you wish to count how many marked elements you have. This is the quantum counting problem. The first version is BHT, Bennett, Hoyer, Tepp. There is a better version by BHMT, Brassard, Hoyer, Mosca, and so now we go beyond the basic quantum algorithm, and let me try to describe the element distinctness problem. So consider a list of n elements. Are all element distinct? This is a computational problem, a binary computational problem. And classically, it requires any queries to the list. In the quantum case, you query n to 2/3 time. So it's not even a quadratic speedup. You go from n to power 1 to n to power 2/3. And there are some previous results by Aronson and Shi, which showed that there is a lower bound n to 2/3 is a lower bound in the query model. So that's the best you can do classically or quantumly, and there is no way better than that. And in 2003, Ambanis described the quantum algorithm with n to 2/3 queries. Here's the reference here. So I'm going to try to describe this algorithm. It's a hard algorithm. The structure is really different from the previous ones. Let n be the number of elements in the list. Let bracket n be the set here. Let R be an integer nearest to n to power 2/3. We are going to use a lot this R. As R is the set of all R subsets of bracket n. And then we need a graph. Called Ambanis' graph. The definition is here. It's very hard to describe. I prefer to give an example. So let's move for an example. Suppose that L is 13, 2, 13, 7. So the answer is yes. There is a repeated element. N is equal to 4. R, we take 4 to power 2/3, nearest integer is 2. So what we have to do? Find all R subsets of bracket n. And then we find all R plus 1 subsets of bracket n. And then we build a bipartite graph. The elements of SR we put on the first part. The elements of SR plus 1 we put on the right-hand side. And now we connect vertices here if the intersection of the vertices has cardinality R. So 1, 2 with this, 1, 2 with that. But those do not connect. Okay, so now we have a graph. And I like this because this is a way of codifying your original problem into a graph. And now we can perform a random walk or a quantum walk on this graph. So this algorithm is an example of how you take the quantum walk model and apply it to a practical problem. And now how the algorithm works. Those are Amban's ideas. The algorithm has two parts, a main block and a subroutine. The main block, you repeat square root of r times. You apply a conditional phase flip operator, and then you call a subroutine square root of r times. The subroutine is a quantum walk. You apply U1, that is a unitary operator that if the walker is on the first part, it shifts to the second part. And then you query the list. And then you apply U2, that is the operator that shifts the walker that is on the second part to the first part. And then you query the list again. And then we repeat that square root of n times. At the end, you measure, make a measurement. So what is the complexity? Is square root of r times square root of r. So the complexity is r. R was chosen to be n to 2/3. And then that's the total complexity. This is the number of times we rerun the algorithm. But we have to check what is the success probability. And the success probability described in Amban's paper is 75%. Asymptotically, I have a paper that I fine-tuned those parameters, and we can get 100%. So now the next one, HHL. That is has a different structure compared to the basic quantum algorithm, and a completely different structure compared with the element distinctness problem. So what is the problem? The problem is, given a matrix A and a vector B, find vector X so that matrix A times vector X is equal to vector B. To implement this HHL algorithm, you have some limitation because you have to represent B inside the quantum computer. You have to renormalize it, rescale it as B over the norm of B. And what will be the output? The output will be the state X described by this expression here. So the output is a quantum state. Is not the entries of the vector X. Usually what you want as a solution of a linear system equation are the entries of X, not a quantum superposition. But that is what the algorithm gives you, gives the state X. So it is supposed to be run as a subroutine, as a larger quantum algorithm. The paper is this one here, Harrow, Hassidin, Light. So let me give a very brief description of this algorithm. So the idea is to get an exponential advantage in the quantum case. So you have to have some restriction on A. A must be Hermitian and sparse, is sparse enough. The number of zeros in each line and column must be large enough. Something like log of entries that are not zero, and the remaining are zero. State B must be prepared in the quantum computing, in the quantum computer. So you have to use state preparation. We know that the general recipe for state preparation is exponential. So if you choose some difficult B here, the algorithm is going to be exponential. The paper gives one application. Since X is the output, they say it is possible to calculate expectation value of some observable. So you create X at the end, and then you choose some observable, and then by repeating the algorithm a few times, you get the average of the observable that you choose, which is an interesting application. So how it works? Let lambda j and u get uj be the eigenvalues and eigenvectors of matrix A. So now we can decompose that vector B into the eigenbases of A. Those are the coefficients. And the goal is to obtain this state here, because this state is the inverse of matrix A. You invert the eigenvalues and apply it to the vector B. So this should be the output of the algorithm. So how do we build a quantum circuit that produces this state? We do the following. So suppose that A has this composition in the eigenbases, R is the eigenbase, the vectors, the columns of R are the eigenvectors of A. D is the diagonal matrix of the eigenvalues. And so we start having A times X equal to B. So the first thing we do is to take this dagger R here to the other side. So we get this expression here. How do we do that? We use the phase estimation algorithm using as U. Phase estimation algorithm has that controlled U. You plug there this operator here. So the next step is to move D to the other side. That means to invert the eigenvalues. And the last step is move R to the other side and becomes R dagger. So this is the circuit. You have to prepare B using state preparation. So the first step here is quantum phase estimation algorithm, Kitaev's algorithm. And here you have to make the inversion of the eigenvalues. This is no trivial stuff. You have to do a lot of controlled operations. And you also have to employ a post-selection here. A post-selection means that you have some extra qubits that you want it in a specific state, 0, not 1. So you have to measure. If you get the wrong measure, you have to repeat the algorithm. So this is called post-selection, and a lot of quantum algorithms use post-selection. And then if you get the correct post-selection here in this phase, you make the last part that goes back to the same eigenbasis of the original matrix. And then you get here your state X. The state preparation is so important, not only for HHL, but for many other areas, and also for quantum machine learning. So what is the simplest recipe for the state preparation? So the idea is that you start your circuit with zeros that you know how to prepare, and you want that the output be B, or be any vector that you want. So the recipe is this one here. You apply R, Y rotations indexed by those angles. R, Y is defined here, and the angles There's a recipe here and how to find those angles. You can look at it in Professor Petroni's book, for instance. And these angles are calculated using the entries of the vector that you have to produce. So it's a very easy recipe to implement in Qiskit or any of those languages. And this is an exponential recipe. Why? For example, here we can see that we have 4 controlled RYs. So if you put an extra qubit here, how many controlled RYs we will have? Will be the double, will be 8. You put an extra, will be 16, and then keep increasing exponentially. So this is not efficient. So there is a big line of research trying to build more efficient circuits for state preparation. And there are contributions from De Newton and Professor Petroni using machine learning. So now variation quantum algorithms. This area started in 2013. I think the first one is this one here, is called VQE, Variational Quantum Algorithm, solved by O'Brien et al. Is a group of Australian researchers. And the goal is to find the ground state of Hamiltonians. Usually is applied for quantum chemistry. And the next one is KOA, Quantum Approximate Optimization Algorithm by Fahey et al., a group of physicists from MIT. And the goal of this algorithm was to improve the complexity of solving NP-complete problems on quantum computers. They had some early success, but they lost the run because people improved classical algorithm, and till now, as far as I know, there is no quantum algorithm based on KOA that's faster than classical algorithms. The next one that's well known is VQLS, Variational Quantum Linear Solver by Bravo Pietro et al., a group of Spanish researchers, and it solves the same problem of HHL, but using a completely different structure, and the goal is to solve it on NISQ computers, while HHL needs a fault-tolerant quantum computer. So the structure is like this, is a hybrid structure. You have quantum operators indexed by those angles phi's. You have to have few of them, so you need few columns because you cannot run on NISQ too many columns. From my experience, you cannot run more than 50 columns. I mean, after decomposing all operators into CNOTs and 1 qubit gates. And then you do a measurement, and this result feeds a classical optimization. You have some cost function here, your objective function, that depends on this parameter. You want to minimize some average of the Hamiltonian, mean energy, something like that. And then the classical optimization parts improve the values of these phi's, and then you rerun with the better guess and rerun it a few times. the goal is to decrease the objective function, minimize the objective function, use this hybrid classical quantum method. Originally, this algorithm was proposed as a quantum algorithm, but people from quantum machine learning borrowed this algorithm because you can train those angles. So they are being used in QML. And now I approach my main area of research, quantum walks. We have a very nice introduction of this area by Salvador, so I'll be quick here. So quantum walk on a graph G with adjacency matrix E is driven by one or more operators that obey the postulates of quantum mechanics and besides locality conditions with respect to the graph. So the area of quantum walks is a sub-area of quantum mechanics because you have to put these extra locality conditions that depends on some graph. The graph has edges, and edges tell you which vertex is neighbor to which vertex. Locality means if the walker is on one vertex, it can go only to the neighboring vertices. It cannot jump, can hop, little hops, hop for neighboring vertices, but cannot jump. Big jumps. So the first example is the continuous time quantum walk. It obeys the first postulate because the Hilbert space is spanned by the vertices of the graph. It obeys the second postulate because the state at time t is ut times the initial condition, where ut is exponential of I gamma at. Gamma is a real parameter that tells you what is the spreading rate of the probability. The walker is on some vertex, and there is a probability that for him to move to the next vertex. And this probability is going to leak continuously to the neighboring vertices. Why this operator is local? Because if you Taylor expand it, you can see that if you take small t, you are going to apply A. If you apply A to the state, the walker is on vertex, you apply A, is going to be to neighboring vertices. If you apply A to power 2, you are going to jump. So if you take t small enough, you forget all those terms, this operator is local. So you cannot choose any operator here. You have to use adjacency matrix or something similar because of the second constraint here. The second example is the discrete time quantum walk. The first postulate tells you that it obeys the first postulate because the Hilbert space is the tensor product of two spaces, one space spanned by the vertices, and the other space spanned by the state of the coin. And it obeys the second postulate because the state at time t is u to power t applied to the initial condition. And now you have to choose what is u. U is going to be a shift operator times a coin operator, tensor I. I is the size of the vertex space. And as the shift operator is defined like this. You apply S to this state. This is the value of the coin. This is the position of the walker. The position of the walker will be V prime. You have to demand that V prime and V are adjacent. And then you obey the restriction. My area of work is mainly quantum walk-based search algorithms. So how do you search on graphs? In the continuous time case, you have to add an oracle. So you have the original Hamiltonian, and you add another Hamiltonian that works as an oracle. The oracle usually is chosen like this, a sum of vertices. Those are the special vertices that are called marked vertices. In the discrete case, what you do, you instead of adding here, you multiply by an oracle. You have your standard evolution operator that I have described in the previous slides, and then you multiply by an oracle, and the oracle has this convoluted expression here, and here appears the sum of the marked states, and this is the description of the quantum walk-based search algorithm when you have many marked elements. In most of the development of this area, people put only one marked element. The first paper that addressed the multi-marked case for the discrete time case is this paper here by myself and two PhD students. It was published in 2021. We recently got published a similar version of this paper for the continuous time case. It was the first paper that addressed the multi-market case for continuous time quantum walk. It has been recently accepted on the transaction on quantum computing of ACM. We have this quantum walk simulator called Hyperwalk. This is the snapshot of the page, hyperwalk.org. So here says that you can, I have to make some inventions here. I can't read. It means that you can simulate quantum walks, continuous time case or discrete time case, and you can use heterogeneous quantum computing, HPC. That means that you can run in parallel on your CPU or GPU cards. It is an open source project. It is built on Python, is a Python package, completely open. It is on the GitHub. You press here and enter in GitHub. We can see that we can test the package here online. Here's an example of a code, so you can copy and put here and press enter, and it's going to run. So you can test the package or Python itself. There is a documentation here, installation, a lot of details how to install. It's very easy to install if you don't want to use the HPC part. If you want to use the HPC part, there are a few steps more, but we use a Docker implementation. The Docker envelops everything in one program. The Hyperwalk package, Python, the HPC parts, and then it is easy to use after that. So I'm going to the end. So as a final comment, I have described a lot of quantum algorithms. There are many more, and this took 3 decades of development. It's really hard to develop new quantum algorithms. We have a few tools. For instance, quantum walk are tools to develop new quantum algorithms. We have the challenge of developing quantum algorithms that are faster than classical algorithms. So it's different from the area of classical algorithm that you sit and program in C. and it is you don't worry because it was the first time. But in the quantum case, we always have to worry if the classical case would be not quicker than the classical case. And even after 3 decades of development, my feeling is that it is just the beginning of the area. Thank you.
Okay, thank you. We have time for questions. 2 questions, I think is have time. Okay.
Okay, Renato, thank you for your talk. I will ask you something that you didn't speak, sorry, but I'd like to know what you think about. Do you know something about quantum signal processing algorithms?
What?
Quantum signal processing algorithms.
Signal
Yeah.
approach.
Yeah, quantum signal processing, this kind of algorithm.
There is a recent review by that co-author of Nielsen Schwang paper on signal processing.
Yeah.
I'm familiar with.
Yeah, I'm asking you because there is a talk by Isaac Schwang in which he mentioned that, okay, there is a unified view of all quantum algorithms, okay, except quantum annealing, in which quantum signal processing, it seems that, okay, is the whole grail of all these things. So I'd like to know if you study this kind of algorithm, if you are interested in. And I see that people in Brazil, they are adopted studying this kind of algorithms.
Yeah, this paper I gave to a PhD student of mine, Pedro Lugão. He has already finished now. He's a teacher here in Cefet, in fact, in Petropolis. And he gave me a series of talks on that paper. We read the whole paper during 3 months, something like that. We understood the paper. And our impression at the end was that it is a kind of, when you change 6 to half dozen, something to very similar. So you see the same algorithm that are there using signal processing terminology. But is this the same algorithm and so on? So if you are very familiar with signal processing, you would prefer to look at quantum algorithm from their point of view. But it's a point of view. That was our conclusion after reading the whole paper.
Okay. My question is because it seems that these kind of algorithms are for long-term quantum computing. They are not for now, and maybe that why people are they aren't paying too much attention. But it seems that they are necessary because when you have quantum error correction, maybe this kind of important algorithms. So my question, if it would be necessary to include this kind of algorithms in our quantum computing courses, for instance.
You mean that signal processing?
Yeah, quantum signal processing.
I think it's not really necessary. No, you mean that grand unification of algorithms, that the paper? I think it's not really necessary. I mean, if you are more familiar with signal processing than that circuit model, so keep do signal processing description. But they are equivalent. equivalent language for the same thing.
Okay, thank you.
Okay, more question? Oh. Renato, thank you for your presentation.
Welcome. Thank you.